Okay, let's do properties of logarithms. So in this section, we'll we'll prove as well properties of logarithms. In particular, we'll consider expressions involving sums of logarithms and differences of logarithms, and we'll numerically approximate logarithms involving bases other than 10 or e. And this has come up in the past where we had logs to other bases, and the calculator, a scientific calculator, will have built in the base 10 log function, the common log function, and the base e log function, the natural log function. So if you want to take logarithms to other bases, we need a way to relate those other logarithms to these logarithms that are in the calculator. So we'll have a formula stated and proved that will establish that relationship. Theorem 5.5.a states some properties of logarithms, largely straightforward. They come pretty much from the definitions of log functions as an inverse of exponential functions. But let m, n, and a be positive real numbers. A is not 1. We'll take a as the base of the log functions, and let r be any real number. First claim is a to the log base a of m equals m itself. This is where whatever the exponential function is doing, it's being undone by the log function, or whatever the log function does is undone by the exponential function. Secondly, log base a of a to the r equals r. Again, it's an inverse function relationship. Whatever the exponential does, the log undoes, and vice versa is the punchline from these first two. And that's how the proof will go. We simply define log functions as inverses of exponentials. Part 3, the log of a product equals the sum of the logs, that is log base a of m times n equals log base a of m plus log base a of n. And remember, a way to keep these properties in mind is meaningful. Logarithms are exponents. So what very informally this says is when multiplying, add exponents. Hey, when you divide, you subtract exponents with a common base. Well, these logarithms are exponents. So that's the reason in products we get sums of logs, and in quotients we get difference of logs. That's the informal reason. We'll go through the formal reason. Fourthly, the log of a quotient equals the difference of the logs. Log base a of m divided by n is log base a of m minus log base a of n. And again, when you divide, you subtract exponents with a common base. And that's certainly related to the reason for this. It's a way to remember it, if nothing else. And fifthly, the log of a power equals the product of the power and the log, that is log base a of m to the r equals r log base a of m. Notice that little exponent inside the log function has come out front as a coefficient. Now, if any of these are surprising, it's this one, but we'll go through and establish each of these. And an additional little observation, a to the r power can be written as a to the r times natural log of a power. This is a conversion of an exponential function to the natural exponential function using the natural log function. And we'll have relations similar to this that don't change exponential functions into natural exponential functions, but change log base a functions into natural log functions, or log to any particular base. So let's go through a proof of that and follow it with a slew of examples. So first up, here's a statement of the proofs. Let's go through these 5, arguably 6 things, since there's 2 of them in the last one. First claim, a to the log base a of m equals m. Well, if we let f of x be a to the x, by definition, the inverse function of f is log base a of x. All this predicated on the fact that, hey, exponential functions are 1 to 1. That's one reason we've taken the base to be not 1. But exponential functions are 1 to 1 functions, so they have inverses. And the inverses, by definition, are log functions. For any inverse functions, we have, by the definition of inverse function, f of f inverse of x equals x. Whatever f inverse does, f undoes, and simply spits out the value x. Whatever goes into the composition comes out of the composition untouched ultimately. And this holds for all x in the domain of the inner function of f inverse. We dealt with that when we introduced inverse functions earlier in this chapter. So in this case, f of f inverse of x, okay, let's see, f inverse is the log function, log base a of x. We will put that inside the exponential function. So we'll get a to the f inverse of x, a to the log base a of x power. Here's the composition of f with f inverse. We know that equals x because these are inverse functions of each other, and that's valid for all x in the domain of f inverse. The domain of log base a of x is x greater than 0. So we get this relationship here. This is basically what we have up here. Replace the x with capital M. And then it reads exactly like this. Well, capital M will have to be greater than 0. Yeah, that's okay. We said M was a positive real number. So that establishes the first claim, simply based on the behavior of inverse functions. Second claim, same thing. We've just composed them in the other order. Instead of having the log function inside the exponential, like in part 1, in part 2, we've got the exponential inside the log function. They're still inverses of each other. For any inverse functions, we also have f inverse of f of x equals x, this time for all x in the domain of the inner function. In this case, it's the function f. So when we look at f inverse of f of x, all right, this time we're putting f of x, the exponential function, inside f inverse of x, inside the log function. So we'll have log base a of a to the x. There's the composition. You know this equals x, and you know this holds for all x in the domain of the inner function f. The inner function is the exponential function. Its domain is all real numbers. And with a little substitution, x equals r for real number, I guess. We get log base a of a to the r equals r itself. And that's the second claim. So these first two properties are simply the fact that logarithms are inverses of exponential functions and the definition of what an inverse function is. Thirdly, the log of the product is the sum of the logs, if you will. So to paraphrase this, and I said, remember this by thinking when you multiply with a common base, when you multiply with a common base, add exponents, and logarithms are exponents. And we're going to prove this using properties of exponents. So set A equal to capital A equal to log base A of M, set capital B equal to log base A of capital N. So represent this as capital A and this as capital B. We want to introduce these extra symbols so we can translate these log expressions into exponential expressions. Rewrite capital A equals log base lowercase a of M, rewriting it as an exponential expression. The base is A, the exponent is capital A, and the output is M. Lowercase a to the capital A equals capital M. Similarly over here, lowercase a to the capital B equals capital N. Simply translating log statements, log expressions into exponential expressions. Why that? So we can use properties of exponents. So if we look at log base A of M times N, that would be log base A of lowercase a to the capital A power, lowercase a to the capital B power. That's what we just established, M and N. So we're just substituting in for M and N, these exponential expressions. Now we got a product of two exponential expressions. When you have a common base, you add exponents. For the record, that's theorem 5.3.a, where we had established that, where A and B were any real numbers. And so multiplication, common base, we'll add the exponents to get A plus B. Now we just saw when we have an exponential function inside a log function, both of them base A, that composition simply yields the exponent. That was property 2 that we just showed on the previous slide. So think of it as the log base a function and the x and the a to the whatever function. Those two, in a sense, cancel. It's not cancellation, it's composition of inverse functions. But the outcome is the same as cancellation. The log base a and the a to the whatever power, those work together to produce an identity function. They disappear. And you're just left with the exponent. That's what property 2 said. And so we're left with a plus b. Now we had a by definition was this quantity, log base lowercase a of m. B was this quantity, so let's substitute those back in. And we get log base a of m times n as log base a of m plus log base a of n as claimed. What made the whole thing work? The fact that you add exponents when multiplying with a common base. The rest of it was just symbols that we had introduced. Part 4 deals with quotients. Excuse me, deals with quotients. And the argument's almost identical. So we'll make the same substitution. We'll introduce capital A and capital B. We'll translate then these log statements into the same exponential statements we had on our previous slide. And then we'll take log base a of m divided by n. That would be log base a of lowercase a to the capital A divided by lowercase a to the capital B. Hey, division with a common base. You know by properties of exponents, again for the record, Theorem 5.3.a, that when dividing you subtract exponents. So this becomes inside the log function lowercase a to the capital A minus capital B becomes this quantity here, subtracting exponents with a division. Now we've got an exponential function inside a log function. Property 2 said those effectively cancel each other, composition of inverse functions, and we're just left with the exponent a minus b. Substitute in for a and b, just like we did before, and there you go. So this is identical to the previous proof, except there's division and subtraction instead of multiplication and addition. This actually also appears as one of the exercises in this section 5.5. Next, log base a of m to the r power equals r times log base a of m, and then another little claim that we'll prove on the next slide. Okay, let's take capital A equals to log base a of capital M again, and let's translate this log expression into an exponential expression. It becomes, again, lowercase a to the capital A equals m. Why do we keep changing these logs into exponentials? Because we got properties of exponentials, and we're developing properties of logs. So we take the question from where we are to where we already know some stuff, and then we translate the answer back. So log base a of m to the r, we know m equals lowercase a to the capital A, so substitute that in, and we get log base a of a to the capital A raised to the r power. Under these conditions, multiply exponents, so we get log base a of lowercase a to the r times capital A, multiply the capital A and the r together. Theorem 5.3.a, that's the property of exponents that we're using to accomplish this. Now we've got log base a, and inside it, an exponential function base a. The log base a and the exponential compose to give the identity function, and yet again, you're just left with the exponent, lowercase r times capital A. And we had capital A in terms of logarithms is given here. Substitute that in, and that's exactly what we were trying to show for this part. So exponents inside log functions come out front as coefficients. The book words it as the log of a power equals the product of the power and the log. Yeah, the power r comes out front and becomes part of a product. And there's one. We also want to prove this extra little piece over here, so let's do that next. So trying to establish this. By part 1, if we take a equals to e, so log base a becomes log base e, or natural log, I'm trying to get the ln of a thing introduced, then by part 1, we had exponential composed with a log function equals the identity. Here, the exponential is an exponential base e, and the log function is a log base e, log base e. So, composition of inverse functions, you're just left with the innermost function. Whenever we use property 2, we were using composition of inverse functions. Whenever we use property 1, we're using the other composition of inverse functions, f of f inverse versus f inverse of f. So they look different. Here we've got the log function inside the exponential. So we get, in this composition, simply m. So if we look at e to the natural log of a to the r, we just showed by part 5, this part here, applied to natural log functions, that exponent r on the a inside the log function comes out front as a coefficient of the log function. I mean, all that happens in this exponent, but all we did was take the exponent and bring it out front as given here, but with a natural log, exponents lowercase r, and that happens within the exponential function. First part of part 5 justifies that. Now we're dealing with an exponential. We know properties of exponential functions, so we're going to rewrite this as e to the natural log of a, r, to the r power. Under these conditions, you'd multiply exponents. Multiplying exponents here would produce this, theorem 5.3.a, again. So that's the equality there. Oh, wait, here we've got e to the natural log of a. That simply gives out a itself. That's what we were saying here. E to the natural log capital M equals capital M. And I replace capital M with lowercase a. And then this in parentheses looks exactly like that, and so simplifies down to the thing inside the natural log function, which is lowercase a, giving us a to the r. And that was the relationship we were trying to establish. A to the r equals e to the r natural log a. So this is allowing us again to convert from an exponential function base a to an exponential function base e, or backwards if you like. It allows us to write exponential functions in other bases other than base a or base e or base 10. That will be useful in particular when we deal with log functions. Now let's look at some examples that illustrate these. Use the properties of logarithms to find the exact value of log base 6 of 9 plus log base 6 of 4. Exact values, that means no calculator stuff. At this stage, just as well, calculator doesn't have a log base 6 button on it. So let's use properties of logarithms, that's the instructions. Here we've got a sum of logarithms. Well, we know a sum of logarithms equals the log of the product. Log of a product equals the sum of the logs, starting with the sum and going to the product. So log base 6 of 9 plus log base 6 of 4 is log base 6 of 9 times 4. This is the capital M, capital N stuff we had in theorem of 5.5.a. So we can combine these two logs as a single log by multiplying what's inside the log functions. 9 times 4 is 36, so this reduces to log base 6 of 36. Oh, well, we're in business there because 36 is a power of the base 6. 36 is 6 squared. So log base 6 of 36 equals log base 6 of 6 squared. No particular reason for that because 36 equals 6 squared. Oh, and here we have a log function composed with an exponential function. They're both base 6. If they weren't base 6, we couldn't do anything about this. Had this been log base 7 here, I have no clue how to do this. We simply can't do that. But since the bases are the same, we've got a composition of a log function and an exponential function. That just leaves the exponent. That was part 2 of theorem 5.5.a. In the next section, we'll do more of these dealing with equations. You simply need to have ultimately in your memory banks the properties of logarithms. It's simply based on the fact that logs and exponentials are inverses. And so we simply get the exponent out. So the answer is 2. Not immediately obvious from what we started with, but the answer is 2, and there's 1. So these questions they ask in the book are totally designed to fall apart with the knowledge that you currently have. Number 36 says, suppose natural log of 2 equals A and the natural log of 3 equals B. Okay, they're just introducing these parameters A and B, I think. Use properties of logarithms to write the natural log of the 4th root of 2/3 in terms of A and B. Okay, so we want to take this expression and write it in terms of natural logs of 2 and natural logs of 3. Here's a natural log, there's a 2, there's a 3, there's a quotient, and there's a 4th root. Fourth roots are exponents, and we know what to do with exponents. So let's take the natural log of the 4th root of 2/3, write it as the natural log of 2/3 to the 1/4 power. So that radical becomes an exponent, definition of 4th root. And Theorem 5.5.8 part 5, first part of part 5, told us you can bring that exponent out front. So that exponent of 1/4 inside the log function comes out as a coefficient, producing 1/4 natural log 2/3. Part 5. If this is too fast, pause it and go back and look at Theorem 5.5.a part 5, where you see the little exponent. We denoted it with an R coming out front as a coefficient. Of the properties of logarithms, this is kind of the most exotic in my opinion. So we get it out front as a coefficient. What were we trying to do? We're looking for log 2 and log 3. So we can make a substitution and express this thing in terms of A and B. Well, we got the log of 2/3. Okay, that's a log of a quotient. The log of a quotient equals the difference of the logs, part 4 of the properties. So the log of 2/3 is the log of 2 minus the log of 3. Don't forget, this whole quantity is multiplied by 1/4, so don't forget the parentheses. So the thing we started with has reduced to this. We know natural log of 2 is represented by the symbol A. Natural log of 3 is represented by the symbol B. So the thing we started with can be written as 1/4 A minus B, if that's what they want A and B to be. And there's the answer in terms of A and B. It's an odd way to word it, but they're giving you suggestions here that this can be done with logarithms only of 2 and 3. You don't need a log of 2/3. You can change that. This 4th root thing, you can get that out of the way. Right? It came out front as a coefficient. How about this one? Write the natural log of, parentheses, x times the square root of 1 plus x squared as a sum and or difference of logarithms. Express powers as factors. More vague instructions would be expand this using the properties of logarithms. So instead of simplifying, we're expanding. Well, log of a product is the sum of the logs, as we know, and we got a product right here. We've got x times this square root thing. So the log of x times the square root thing will be the log of x plus the log of the square root thing. So we split that up. So we got a sum. It says express powers as factors. Well, that square root is effectively an exponent, a power. So we can take the log of 1 plus x squared, square root of, and write it as the log of 1 plus x squared to the 1/2 power, the 1/2 being inside the log function. When you have an exponent inside a log function, it comes out front as a coefficient. So this becomes natural log of x plus 1/2 log 1 plus x squared. Can you go any further? You know anything about the log of the sum? You do not. You know things about sums of logarithms, but not logarithms of sums. This can't be broken down any further, in other words. So don't make up your own rules. You only got 5 rules that you can use. You make up your own rules and you're on your own. You're probably doing it wrong. follows the properties as we stated in Theorem 5.5.a. So don't make up your own rules and you're fine. Logarithms are exotic beasts, but as long as you simply use the properties that logarithms follow, you'll be fine. So you're stuck here. Can't go any further. We don't know anything about the log of 1 plus x squared. So that must be this original expression expanded. And it's a sum of logarithms. And here's that factor idea they're using. The power of 1/2 is introduced as a factor coefficient more appropriately. How about this one? Same idea, but a little bit more complicated. Right, natural log of 5x squared, cube root of 1 minus x, all divided by 4 times x plus 1 squared. X is between 0 and 1. What's up with that? That must ensure, I'm going to trust them on this, that must ensure that we're not taking logs of negatives and we're not taking a logarithm of 0. We're not dividing by 0. Cube roots, you got a problem with cube roots. We can take cube roots of negatives. We can't take logs of negatives though. So I'm trusting this is a valid part of the domain of this log function. Okay, write this as a sum or difference of logs, express powers as factors, that is expand this out using the properties of logarithms. Okay, so we'll just go through those properties, starting with the quotient. You want to start with something else, start with something else. I'm going to start with a quotient. And we have the log of a quotient. That would be the log of the numerator minus the log of the denominator, property 4. Log of a quotient is a difference of logs. Let's see. Here's two products right here. 5 times x squared times the cube root of 1 minus x. So we can expand that as log 5 plus log x squared plus log cube root. Blah, blah, blah. Over here, we've got a product. 4 times this. So we can write this as the log of the first plus the log of the second. When multiplying inside the log function, add the logarithms. Be careful with a minus sign right here. Notice the parentheses. So I don't want to lose a negative sign. Property 3. We could deal with exponents. Here's an exponent we'll need to deal with. Here's an exponent we'll need to deal with to do their express powers as factors idea. Oh, and the cube root thing, let's write that as a 1/3 power. So the only difference between this line and this line is the 1/3's been introduced. Now we'll take care of all the exponents at the same time. Exponent inside a log function comes out front as a coefficient. 2 comes out front. 1/3 exponent in a log function comes out front as an exponent. The 2 here inside the log function comes out as an exponent. Let's also distribute the negative sign. We'll pick up a negative right there as well. Again, careful with the parentheses. And we get to this stage here, and let's put that in a box because that's the final answer because we can't go any further. Again, you can expand the log of a difference or the log of a sum. There wasn't a property that dealt with that. The log of 1 minus x is the natural log of 1 minus x. There's no expanding or simplifying of that. And so the original expression can be written in this form. It's expanded as sums or differences of logs with any exponents written as coefficients. Right, each expression is a single logarithm. Okay, this time we're going backwards. So they've got this stuff that's been expanded out in a sense, and we're going to glue it back together. So we're going to combine using the negative sign here. For example, number 62. Let's take the log of x squared plus 3x plus 2 minus 2 times the log of x plus 1. By the way, what's the base of this log? Must be base 10, common logs. We agreed to use these symbols when we had common logarithms. So these must be common logs. It doesn't matter. All logarithmic functions have the same algebraic properties given in Theorem 5.5.a. But the intention is these are logs base 10. Okay, we got a difference. Well, not exactly, the 2's in the way. So we don't have a difference of logs because the 2's in the way. We'll get it out of the way. Let's take this 2 and make it an exponent. So take 2 as a coefficient on a log and make it an exponent. That's part 5 of the theorem, the 5th property of logarithms. Instead of bringing the exponent down, we're putting it back up there. It's a two-way process. So we get the 2 as an exponent inside the log function. Now we've got a difference of log functions. The difference of log functions combines to the log of a quotient. Again, the property we've used before, but going backwards this time. Property 4, log of the quotient is the difference of the logs. So the difference of the logs is the log of the quotient. So we've got the quotient here. I'd say maybe that's the answer. Looks like we can simplify this a little bit more. X squared plus 3x plus 2 factors to x plus 2 times x plus 1. I need two things that multiply to give 2 and add to give 3. 2 and 1 works. So the factoring in the numerator is correct. Oh, and then we got an x plus 1 in the numerator and the denominator. This one term can be canceled with one of these terms down here to leave us with x plus 2 in the numerator and a single x plus 1 in the denominator. So it did simplify a little bit more than that. And they wanted us to write it as a single logarithm. There you go. It's a single logarithm. Arguably, it was a single logarithm at this stage here, but let's simplify it a touch more just because we can. Number 70 next. Okay, they give us, let's see, coefficient of a log function minus coefficient minus. Okay, we're going to use the negatives to get quotients. The coefficients will have to go first and become exponents, just like in number 62. So we'll take the expression they gave us. First thing we'll do is take this coefficient and make it an exponent, producing a cube. Take this coefficient, say of positive 2, make it an exponent. And we get 2x minus 1 squared. You want to take the negative sign with it? Go right ahead. I'm going to simply take the positive part and then leave the negative out front, but I don't have to do it that way. And nothing can be done with this term over here. Now we have a log function minus a log function minus a log function. Let's combine them. First, these two. Difference of logarithms is the log of the quotient. So this becomes a numerator and this the denominator in that quotient. Again, we've got a difference of logarithms. Again, we'll have a quotient. So we'll take what's inside here and divide it by what's inside here, which is simply x. So we're dividing this by x or multiplying by 1 over x. That x settles itself in the denominator. And we get this kind of thing here, simply using properties of logarithms. The only thing I can point out occurs to me is all these have to be logs to the same base, right? If we had log base 5 mixed with log base 10, we can't combine them. That wasn't the properties. We had to have logs to the same basis, and they will give us problems of that sort. Let's return to the notes. And let's see, we went through this bunch of examples. The next result follows from the fact that log functions are one-to-one and are functions. The book chooses to state this as a property of logarithms. Okay, let m and n and a be positive real numbers and a is not 1. So usual situation. If m equals n, then log base m equals log, excuse me. If m equals n, then log base a of m equals log base a of n. Yeah, it's a function. When you put the same thing in, you get the same thing out. It's a function. So this part, not too impressive. The other part, somewhat impressive. If log base a of m equals log base a of n, then m equals n. So what we're saying for the log function is, if you get the same value out, if the log of this equals the log of that, then you must have put the same value in. Then m equals n. That's the property, as it says up here, of one-to-oneness. And remember, logarithms are one-to-one. Why is that? Consider the graph. Satisfies the horizontal line test. That's why. They have an inverse. Only one-to-one functions have inverses. The inverses of the log functions are the corresponding exponential functions. So this is just a statement of the one-to-oneness. In some sense, it allows us to solve equations involving logarithms. So that's how we'll use it. A final observation, and we'll do a few more examples. If you look at a standard scientific calculator, it has keys for the common logarithm and the natural logarithm. If you want to numerically approximate logarithms to other bases, you ain't got a key on the calculator. But it turns out you can convert those other bases into base 10 or base E. And that's the buttons on the calculator. And in the following result, we have, it's called the change of base formula. It says if A is not 1 and B is not 1, and A, B, and M are positive, so M will be the input of a log function. A and B will be bases of various log functions. So that's why the condition positive and not equal to 1. The claim is log base A of M equals log base B of M divided by log base B of A. All right. What we've got on the left-hand side is log base A. What we've got on the right-hand side is log base B. So you've changed the base from log base A to log base B. For example, and in the 3 examples we'll do below that require this, we could use B equals E and let these be natural logarithms. Or we could let B equal 10 and let these both be common logarithms. There's a button on the calculator for log base 10 and log base E. So this is how we could calculate logs to other bases. We could use the base E. We could use the natural log function in this little formula. For example, let's actually go through the proof of that. Straightforward. We want to establish this proof. So first, let's introduce y equals log base A of M. And let's translate this log expression into an exponential expression. This is how we prove most of the stuff we've done in this section. Y equals log base A of M means A to the y power equals M. A to the, little typo there, A to the y power equals M. Excuse me, I'll get that corrected in the notes. Then when we look at log base B of A to the y, well, when I correct this, A to the y equals M. So we'll just substitute for A to the y the M parameter, and we get this is log base B of M. Also, log base B of A to the y, you know you can bring that coefficient, that exponent y out as a coefficient. Property 5 of logarithms. So from here to here, we're simply bringing the y out front. The right-hand side remains unchanged. Now we're going to take this, solve for y by dividing both sides by log base B of A. That'll leave y on the left-hand side and a quotient on the right-hand side of this. Y itself was log base A of M. Substitute that in, and there's the formula. So looks like really the theoretical result that makes this work is that thing about bringing exponents outside of logs. And that's effectively what we've done, is use that property 5 of logarithms. But here's the equation allowing us to convert log base E to any other base you want, as long as those bases are positive and not 1. Use the change of base formula and a calculator to evaluate, roughly approximate, log base 5 of 18. They even say rounding answer to 3 decimal places. Log base 5 of 18. There is no log base 5 button on the calculator. So we've stuck with using the change of base formula, which states this. All right, so let's take A equals 5 and M equals 18, then log base A of M becomes log base 5 of 18 upon substituting that on the left-hand side. So it produces the correct thing. On the right-hand side, let's let B equal E. So we can use the natural logarithm function. So you could choose anything you want for the base on the right-hand side as long as it's positive and not 1. Use E because there's a button on the calculator. Use 10. There's a button 10 on the calculator as well. You'll get the same ultimate answer. So on the right-hand side, we'll have log base E of M, 18. In the denominator, log base E of A, which is 5. The base on the left-hand side is 5. Notice that base appears inside this log function on the right-hand side. If you like, we could write that in the natural log notation, natural log of 18 divided by the natural log of 5. And from here on out, it makes no particular intuitive sense. But when you get the calculator out and hit the buttons, natural log of 18 is something like this. Natural log of 5 is something like that. Take the quotient, round it to 3 decimal places, and you get 1.796. So there's how to convert from one base to another. You're unlikely to encounter logarithms to any bases other than base E and base 10. That is natural logs and common logs. Your future mathematical experience, you're actually likely only to encounter natural logarithms. Again, what's natural about them, that's a story for Calculus 1. But natural logarithms and natural exponentials will dominate in calculus throughout. You take a probability class, and the natural log and the natural exponential will play a bigger role than any other exponential functions. You will encounter maybe some other exponential and log functions, but that'll be rare in a calculus class. In a math or statistics class, that'll be rare. The log base 10 stuff is most often encountered in Richter scales, decibel scales. Stellar magnitude is a base 5th root of 10 or something like that. There's a few scales out there that are based on logarithms other than base E. But other than that, you're likely just to deal with the natural logs. So that's why, even in this question, the emphasis on natural logs. And next, let's find the value of log base 2 of 4 times log base 4 of 6 times log base 6 of 8. Find the value exactly. Okay, it must be something special. These bases are all different. It's product of logs. That doesn't help any. What I can do is change these into some common base and see if that leads to something. So let's use the change of base formula. So we change the base of each logarithm, say to base E, to natural logs. Log base 2 of 4 will become the natural log of 4 divided by the natural log of 2. Natural log of 4 divided by the natural log of 2. So log base B, we're going to use natural log. What we'll do is put the M and the 1 in the numerator and the base A and the 1 in the denominator. So log base 2 of 4 would be the natural log of 4 divided by the natural log of 2. Log base 4 of 6 would be the natural log of 6 divided by the natural log of 4, where the pieces go. Log base 6 of 8 will be the natural log of 8 divided by the natural log of 6. So that produces this. Some stuff cancels, I see now. These two cancel and these two cancel, leaving us with the natural log of 8 divided by the natural log of 2. Anything sound familiar there? 8 is 2 cubed. So we could replace the 8 with 2 cubed. We could bring the 3 out front. Says who? Property of logarithms, part 5. Exponents inside log functions come out the front as coefficients. So we could bring the 3 out front. And then even the log base 2 cancels. And the answer is 3. So it was, in some sense, a bit of a trick using the change of base formula. You can't lose by writing things in terms of natural log functions. And lo and behold, by doing that, but we could have used base 10 and similar things would have happened. Everything canceled and we ended up with simply the expression 3. Not very intuitive that this was going to simplify down to 3. Of course, this is a textbook example designed to simply dissolve and simplify quite a bit. And one final example, show log base A. This is just an illustration of log properties. Log base A of square root of x plus square root of x minus 1 plus log base A of square root of x minus square root of x minus 1 equals 0. So establish this equality. We'll start with this expression and manipulate it till we get 0. Notice what's inside the log functions: plus a square root and minus a square root, which is pretty suggestive in itself. We've encountered these things in Precalculus 1 algebra several times. In particular, maybe rationalizing denominators. We saw things that remind me of this. Okay, so we'll start with what's given. We'll start with the left-hand side. And how about this? Let's multiply by the square root of x minus the square root of x minus 1 divided by itself inside this first one. Let's multiply by the square root of x plus the square root of x minus 1 over itself inside the second log function. Why? Well, that's one reason I want to do this one. It's a bit of a trick, but we did do some things similar to this when we were rationalizing denominators in our distant past. I've simply multiplied by 1 inside this first log function and multiplied by 1 in the second log function. You might debate my motivation. All I can plea is, well, we did this kind of thing when we were rationalizing denominators, but you can't question my validity. I can just multiply by 1, so that doesn't change anything. We certainly still have an equality. Motivation for this is a little weak, but the fact that this holds, it's certainly true. If we multiply out here, this is the reason for doing this, we'll have the first one squared minus the second one squared. Foil this with a numerator, you'll get the first one squared minus the second one squared. The outer inner stuff will cancel out. So we'll be left with x minus 1, being careful to keep up with the parentheses in the numerator. In the denominator, you still get this ugly thing here. What you going to do? Similarly, here, we'll get the first one squared minus the second one squared over the complicated denominator. So what we really done here is we really rationalize these numerators. Hey, x minus 1 is just 1. We'll get 1 in the numerator here. It's the same thing. We get 1 in the numerator there. Okay, no problem. We haven't touched the log functions yet. We've just done some weird algebra, but you can't argue with the validity of it. Here we've got a sum of 2 log functions. Well, the sum of 2 log functions is the log of the product of what's inside them. So when we go to the next slide, we'll take the log of this times that, using logarithmic property number, I think it was number 3. Yeah, number 3 says the sum of those logs is the log of this product, what was inside the first log function times what's inside the second log function. And look at this, the denominators, you get that first one squared minus second one squared thing again. The square roots all disappear ultimately. And we get x minus 1 again. But x minus 1 is just 1. We got log base A of 1 over 1. We got log base A of 1. That's 0. The logarithm of 1 to any base is 0, any appropriate base, because a to the 0 power equals 1. And all logarithms are exponents. 0 is the exponent you put on a to produce the value 1. So this is rewritten as an exponential statement of this form, and you know this to be true. And we were trying to show that we get 0 out of this, and indeed we do. It started with the left-hand side. We did our manipulations, granted weird ones on the previous slide, and a logarithm one right here, and a little more algebra, and it simplified down to 0, and that was the plan. And that takes care of this section. What's next is more equations. We've dealt with equations involving logarithms previously, but there was always some kind of little trick to the way we dealt with those. We know a bit more stuff now, And so we can deal with more diverse equations that have logarithms and exponentials in them. And that's the content of the next section, and I will see you there. Have a nice day. Bye-bye.